My project title is Image Synthesis Using Latent Diffusion Models. So basically what this does is it kind of takes an input from the user, the text as an input from the user, and generates an image as an output. So one of the specialities is that this is not one of those models which would kind of pull the image from already existing data source or from the net. The model kind of generates the image. So we'll be looking into how that happens here. So we have to understand the concept of what a diffusion model is and what a stable diffusion model is. So starting off with, a diffusion model is something which generates data similar to the data that it is trained on. So if you just specify it as stable diffusion, it just helps us understand that the output is in the form of image. So we have to understand what forward and backward diffusion is. So forward diffusion is a process where we kind of start off, we take an image and then we kind of keep adding noise to the image to an extent that the image is just left out with a noise. So we are just left out with a noisy image. So when we are adding noise to the image, we kind of keep track of how much noise is added. And then we have a concept of reverse diffusion, where exact same reverse thing happens. Like we have a completely noisy image and then we kind of try to remove the noise from the image gradually. So again, we keep track of how much noise is being removed. So to keep track of this, we kind of use a concept of noise predictor. So noise predictor is basically a neural network uh, model. So what it does is, whenever we are removing a certain amount of noise from the image, we kind of uh, you know uh, help the neural network model to understand what's actually going on. So the whole scenario could be tuned. The neural network model could be tuned with the help of weights and the actual answer, like how much noise is being removed. So this cycle happens until the clear image is obtained. And yeah, as already explained, this model doesn't pull the image from already existing data source. What it does is kind of generates the image. So that's one highlight. And then so in this project, we'll be working on something called as latent space. So usually the models run in a pixel space. We have two different terms for pixel space and the latent space. Usually the models run on the pixel space, but then in case of stable diffusion, it runs on a latent space. So what a latent space is, we have a pixel space, which is the actual image space. So in case of latent space, the information, the important information, it's the lower dimensional representation basically. So only the important information are pulled from the pixel space and put into the latent space. This kind of helps us to speed up the process of training the whole model, which might take a really great time if it is in the pixel space. So that could be spoken about in the literature review. And then we have the input flow. So if we kind of think about what's happening behind, like how a text is sent into a model and then we be getting a image. So what happens is, we'll be starting off with a text prompt and then go ahead with the tokenization. So tokenization is a concept where uh, the the system understands what we are saying, what the user prompt actually is. So the tokenizer kind of converts the prompt into a system understandable number, and from there we'll be having the concept of embeddings. So embeddings are a concept which helps us understand the relationship between the words so that the prompts are better understood. And from there we'll give the output of embedding to the text transformer, and from there to the noise predictor, so that the noise predictor helps us understand how much noise should be removed gradually at each stage. So this is the data flow. Whatever text input flow we've discussed, uh, could be better understood here. For example, if we have the Paradise Cosmic Beach as the input, and then we have the text encoder, we have this text embedding, this text embedding portion here, and then we have a random noisy image. So we'll have a text prompt embedding, and then we'll have a noisy image. Both of these are given to the noise predictor. So we can see that how both of these are given to the noise predictor, and then the diffusion process takes place here. So this is how the noise is subtracted at each level. So the first we'll have the token embeddings and then noise image. In the first step, a certain amount of noise is removed. We'll see if the desired output is obtained or not, and then we'll just continue with the process until and unless the desired output is obtained. So once the processed image information is obtained, we'll send it to the autoencoder to convert it from the latent space back to the pixel space. So though we are kind of operating in the latent space, what happens is we'll during the training process, we'll get the pixel space into the latent space, we'll work on the latent space, and then before generating the output, we'll kind of uh, turn the latent space into the pixel space. And then we have the data collection. So the data collection for this model, the model is trained on a humongous amount of data. So these data, as we could see in the picture, the data set consists of a huge number of pictures and then the corresponding captions. So that is how the model is trained on. And then we have yeah, as already said, this is how the forward diffusion process works. We kind of start off with the image, and then we keep adding noise to the image until and unless we are just left out with the noise. And then we have the concept of latent diffusion, as we've already discussed. It's one thing to be noted is the latent diffusion comparatively is 48 times smaller than the actual pixel space. This kind of helps us to speed up the processing, uh, speed up the process basically. And then we have the system architecture. So this is the system architecture as we've discussed in the previous steps. Yeah, and then the diffusion models, as already discussed, diffusion models are something that would help us generate data, something similar to based on what it is trained on. And then we have the reverse diffusion, as already said. Reverse diffusion kind of helps remove the noise from the noisy image and then helps us reach the desired output. And then we have the concept of variational encoders. So basically, this has two parts. One is the encoder part and the decoder part. So the encoder part helps us to, compress an image to a lower dimensional representation in the latent space. And then the decoder does the opposite, which restores the information from the latent space. And then we have the conditioning. So conditioning is one of the main concepts that kind of acts as a bridge between the text being converted into an image. So this kind of acts as a steering for the noise predictor to help us reach the desired output. Like based on whatever prompt we are giving, the output is generated. So conditioning plays a really important role in that. Coming to the coding part, we start off by installing different packages. So we have the transformers, diffusers and the transformers for various encoding and decoding process that we've discussed. And then there are a couple of other import statements here. So the models that we'll be using in this project are all imported from the Hugging phase. And then we do download a couple of models here, starting off with the autoencoder model, which will be used to decode the latents into the image space. And then we have the tokenizer model, and then the unit model. This kind of helps us generating the latent space. And then we have a couple of functions, starting off with the first one, get text embeds. So we'll start off by sending a prompt here, and then we tokenize the text and get the embeddings here. So once the embeddings are obtained, they are sent into the very next function. Here, so as we've already discussed, we'll be having two things. That the first one is the prompt that the user gives, and the second thing is a noisy image. So both of these are sent, and then from there the tuning happens, and then we'll be getting the output image. So this is the text embedding, and then this torch.random kind of helps us to generate the random noisy image in the latent space. So once this is obtained, from there we'll be giving that into the noise predictor. Noise predictor helps us understand how much noise is to be removed at each step. So we can see here that we are proceeding towards uh, the output. So at each step will be resulting towards the output. And then this is a couple of scaling, how do we scale the output. And then we have whatever functions we've defined and used, we'll be calling it here in this block. So the first will be sending the prompt to the prompt to image function. From there we'll be, whatever output we get, we'll be sending that the prompt to text embeds. So this kind of helps us to convert the prompts into the text embeddings. After that, we'll the text embeddings, whatever we obtained, will be converted into the image latents, and then we'll convert the image latents into the images. So, and then the image is returned. For the front end, I've used Gradio. So this is how the interface looks. So we can give a prompt here. The more detailed prompt we give, the more detailed image we'll be getting. So we can give a really detailed prompt here. When we click on submit, we'll be given an output of image related to our prompts. And then, yeah, as shown, this is how the deployment looks. This is how the output screen looks like. We can give a detailed prompt, and then the image is obtained. So these are few other things I write out on my model. So conclusion, the whole concept of latent diffusion has actually helped us to work with all of these models, say in our laptops, because if not, working with the images in the pixel space would be really difficult and would require a greater GPU supports, which might not be really possible for everyone of us. And then apart from that, this concept of stable diffusion could be pushed into the applications, like it could be integrated into the applications, and then we can kind of use it from there. Like for example, Photoshop, we could kind of put an image or text into it and beautify it. And then it's even used in painting and out painting. Like if we have some image, and then lost its features or the color, it could be pushed into this model, and then we could expect a better picture of it. So moving on to future scope. So though this model works fine and all, it has few limitations. Like compared to other models of the similar kind out there, stable diffusion kind of understands the user prompts in a better way, but then the output that is generated could not always be as precise as possible. So we cannot really expect the output that is super precise with respect to the user prompt. And the other limitation is uh, the data that it is trained on is just scraped from the web randomly. So the problem of using others' art might be a concept of consideration. So these are few of the references. That's it. Thank you.